Okay, so we have seen that if you have a function f of x with period 2 pi, it can be expanded in a Fourier series in terms of cosines and sines. And we have seen also how this can be thought of as an expansion of a vector in an orthogonal basis, right? So where cosines and sines can be thought of as, unit vectors which form or the vectors of a basis, of an orthonormal basis, and then working out the Fourier coefficient is really an exercise in working out the expansion of a vector in terms of its basis vectors. Right, so in this lecture we will look at an example of how to carry out this expansion in practice. Okay, so we are finally ready to write down the prescription. We have already written down the prescription, but given so right now forget about the abstract perspective which we have already brought in, right? So if you think of this as a function with period 2 pi, we can expand it as in this manner, and where the coefficients are given by this, right? So this is to be viewed purely as a prescription. You have a function f of x period 2 pi, right? And so we want to find a bunch of coefficients a0, a1, a2, a3, so on, and b1, b2, b3, and so on, such that we will be able to say f of x is equal to this expansion, this infinite series, which is called a Fourier series, right? So the prescription is simply given by this. You have to do 1 over pi integral minus pi to pi f of x times cosine of n of x dx, and bn is 1 over pi integral minus pi to pi f of x sine of nx dx, right? So this is the prescription. If you are interested in just purely the Fourier aspect, the operational aspect of it, so this is what you will have to keep in your head, right? So you're given some function f of x like in the following example. Suppose you're given this function f of x which is 0 from minus pi to 0, and it's 1 from 0 to pi, and it repeats, right? So if we invoke this above prescription, right, so you have to be careful with this, right? If you blindly do this, you might think that all the a_n's are 0, but in fact a0 is to be treated slightly differently. So the integral minus pi to pi reduces to an integral from just 0 to pi, because f of x is 0 in the interval from minus pi to 0. So it's minus 1 over pi integral 0 to pi 1 dx, right? So this will just give you pi, and go divide by pi is just 1. So a0 is 1. But if n is greater than or equal to 1, an is 1 over pi integral minus pi to plus pi f of x cosine of nx dx, which is 1 over pi 0 to pi cosine of nx dx. And now you see you get a 1 over n pi sine of nx 0 to pi, but sine is going to be 0 both at x equal to pi and x equal to 0, right? Unless n is 0, which we have already seen, right? That's a separate case. You cannot blindly put it into this. So an is 0 if n is greater than or equal to 1, and bn likewise is an integral which needs to be evaluated only in the limit of in the interval 0 to pi, right? Because of the function that we have, f of x is 0 in the intervals minus pi to 0. So we have 1 over pi integral 0 to pi sine of nx dx, which gives us 1 over n pi minus cosine of nx from 0 to pi. So now we see that unless n is odd, right, this is going to vanish, right? If n is even, so like n equal to 2, for example, then you see you get 1 minus 1 divided by 2 pi. It doesn't matter, it's going to go to 0. So if n is odd, you'll get 2 in the, so you get 2 divided by n pi if n is odd. Otherwise bn is 0, right? If you put all this together and we can plot this, right? So the function looks something like this. I have plotted I have kept terms up to sine of 9x, right? So it's going to have only signs in it. There is a constant term half, then you get 2 by pi, then you have sine x plus 1 by 3 sine 3x plus 1 by 5 sine 5x, so on, right? It's 1 over n times sine of nx, where n takes only odd values, and then there is this factor 2 by pi outside, right? So let's look at what this function looks like if I plot are truncating it up to this term. So you see that indeed it works out very well, right? So the actual function is something like this. It's 0 in this region, and then it's going to be 1 here. So let's keep on reducing the number of terms. So if I take this only up to 4 terms, then it looks like this. Yeah, so it's not too bad. It's already looking like the original function. So, this too is is indicative of the original function. Let's remove one more term. Yeah, it's already it's decent considering that you have just kept 3 terms in this infinite series, and it's able to mimic your overall function. Let's see what happens if I remove one more term. That's just the sign, right? So it's not great, but it has the broad properties are in there. Of course, if I remove this also, then that will be just that's like the DC term, it's called, right? So it has no so it just gives you the average value. Of course, this is bad, but that's what you would expect if you try to take a whole function and put one number to it. Okay, so this lecture was an exercise in giving you an operational example of how, if you're given a function f of x which is periodic with period 2 pi, this prescription, it works, right? So I have considered a simple example, and then it will be part of the homework to work out many such examples and become very familiar with the just the operational aspect itself, right? So that's all for this lecture. Thank you.